Hello. So today we're going to start talking about the opposite of derivatives or antiderivatives. So this entire time you've been in calculus, we've talked a lot about taking a derivative, how to do it, all the different rules and properties, and what you can do with derivatives. So now we're going to start working backwards with antiderivatives. So as a definition, we say a function capital F of x is an antiderivative for little f of x if the derivative of capital F of x is equal to little f of x. So that means if we take the derivative of some function, we get back another function. So something to consider is the fact that antiderivatives are not unique. So antiderivatives not unique. And here's an example of why. So let's let big F of x be equal to x squared plus 2 and big G of x be equal to x squared minus 1. So if we take the derivative of both of these, so if we find big F prime of x, we know that that's simply 2x. Now if we find big G prime of x, that's also just 2x. So they're both equal to little, so big F prime of x is little to little f of x equaling 2x, which is also equal to G prime of x. So those constant terms that we throw on, they make them not unique. So whenever we talk about antiderivatives, unless we give you certain conditions, we're talking about a family of infinitely many antiderivatives, and we'll see how that works out next. So to find antiderivatives, we use what is called an indefinite integral. So f of x is equal to the integral of little f of x dx. So this right here is your integral sign. And we actually need to change something about the notation that's on the board, because an indefinite integral considers all possible antiderivatives of this function little f of x. So what should really be written over here is that the indefinite integral of little f of x dx is equal to big F of x plus c. And this is called our constant of integration. And putting that there, which is really important for indefinite integrals like this, it's really important to do because that c represents the whole family of possible antiderivatives. So it could be any number, positive or negative, it could be a fraction, decimal, whatever, that would make that this big F of x an antiderivative for little f of x. So then we need to talk about this dx right here. So this is really important because it tells you what variable that you're integrating over, and it also tells you where to stop integrating. So this is your stopping point for integration, and it tells you what variable you're using, which isn't very important for you guys right now in Calc 1 or Calc 2, but if you were to go on to Calc 3 higher math, it would matter. Okay, so now you're probably thinking, okay, I know what an integral is, but how do I do it? So we have some integration rules for you, and the most important one is going to be this power rule. And as you continue on in Calc 1 and Calc 2, you'll learn a lot more integration techniques and rules, but this is the primary one that you're always going to go back to. So for the power rule, it says that if we have some indefinite integral of x to some power n dx, so n is a number, and it can be positive, negative, fraction, whatever. But the only thing it can't be is n cannot equal negative 1. And we'll see why in a second. So if n does not equal negative 1, all you do to find the antiderivative is you set up a fraction, and in the top it's going to be x to the n plus 1 over n plus 1, and then plus c for our constant of integration. So it doesn't work when n is negative 1 because then you would get a 0 down here in your denominator, and you'll learn when you get further on. It's one of the first things you're going to learn in Calc 2, what the antiderivative rather, of x to the negative 1 is. So then just like we had constant, sum and difference, and trig rules for differentiation, we have them for integration as well. So the constant rule just says if you have some constant c multiplied by f of x dx inside of an integral, just like you could with derivatives, you can pull that c right out and then just look at the integral of f of x dx and multiply your c in at the end. And then same thing for sum and difference, just like with derivatives, how we could split them up. We can do the same thing with integration. So that's the same thing as the integral of little f of x dx plus or minus the integral of g of x dx. So we can distribute that integral sign to both functions. And then the trig integrals, they're not so much as rules as things that you need to memorize of how to work backwards. So we have 6 of them to go over, and these are something that maybe you want to make flashcards for or anything like that, and just run through them every day until you get them in your head. So the first one we're going to do is the integral of sine of x dx. If we think, okay, what function gives us a derivative of sine, we think about cosine, but we have to remember that the derivative of cosine is negative sine, so the antiderivative of positive sine is negative cosine. And then we have the derivative of cosine of x dx, which is just going to be sine of x plus c. Then we have the integral of secant squared x dx. And if we think about what trig function has a derivative of secant squared, that's tangent of x. So that's one way you can try to think about how to do antiderivatives, doing integrals, is think about, okay, what would I have to take the derivative of in order to get back whatever is inside my integral? And then we have secant x tangent of x dx, which is just equal to secant of x plus c. And then we have 2 more. So then we're also going to have cosecant squared of x dx, which is just going to be equal to the negative cotangent of x plus c. And then for the last one, we're going to have cosecant x cotangent of x dx, which is just negative cosecant of x plus c. So like I said, these are things that you just really have to memorize, and you can kind of think of how to work backwards if you try to figure out what function you'd have to put over here in order to take the derivative and get back what you had in here. So that can sometimes help you out. But running through flashcards and really working on memorizing them is going to help you out for problems. So speaking of problems, let's do a few examples to see how all of these rules work. So the integral of x to the 4th dx. So this is going to be our standard power rule. So all we're going to do for this is we're going to set up that fraction. We're going to do x, and then we just do 4 plus 1 over 4 plus 1, and then you add your constant of integration there on the end. So then we're just going to be left with x to the 5th over 5 plus c. And if you're ever confused on if you've done the problem correctly, a great way to check yourself is to just take the derivative of your answer. So if we take the derivative of x to the 5th over 5 plus c, we use our power rule of differentiation, we'd bring that 5 down, and we would get 1/5 times 5 times x to the 4th plus 0, because a derivative of any constant is just 0. And then this 1/5 and 5 are going to cancel out. We're going to get x to the 4th, which is great because that's exactly what was in here. So since these two things match, this answer must have been correct. So we can check it that way. So that's one really great thing about why you've been doing so much differentiation and working with derivatives so often, is now you can use all of that knowledge to check your integration skills, which is great. So now we're going to integrate 2 times the square root of x. So the first thing we might want to do is pull that constant out and write it out front. And the second thing we might want to do is, just like when we were taking the derivative of the square root of x, we might want to rewrite it so it's a power instead. So we'll write it as 2 times the integral of x to the 1/2. And that's because just like when we rewrote it to take the derivative of it, it made it a lot easier to use the power rule of differentiation. Writing it like this is going to make it a lot easier to use your power rule of integration to work backwards. So your tricks for right now, since you're just learning how to integrate, are really always going to be to work backwards towards the power rule, because it's the only real rule you know other than just memorizing those trig integrals. So now we're going to get 2 and apply our power rule here. So we're going to do x to the 1/2 plus 1 over 1/2 plus 1 plus c, which is just equal to 2 times x to the 3/2 power over 3/2 plus c. Now, we don't want to leave that as x to the 3 halves over 3 halves because that's a complex fraction. But when you divide by a fraction, it's the same thing as if you flipped the fraction over and had it multiplying by it. So this is really just 2/3 x to the 3 halves plus c. And now if we multiply it through by 2, we're just going to get this is 4/3 x to the 3 halves plus c. Now you might say, why didn't you write 2c? I could have, but 2 times a constant is just another constant. So one thing you could do is label this, the first c up here as c1, and then put a c2 down here to recognize the fact that they're different values. But if you just leave it as c, it's fine. It's just an arbitrary constant, so you'd be able to solve for it if they gave you anything else. So now we're going to take some time to do two slightly harder examples. So for the first one, we're going to use that sum and difference rule. So we're going to just split up this integral. So we're going to make it the integral of x cubed dx plus the integral of the sine of x dx. And whenever you split integrals up, you want to make sure to write that dx with all of your terms. So now for the first one, since it's just x to a power, we're going to use our power rule. We're going to x to the 3 plus 1 over 3 plus 1 plus, we just learned that the integral of sine of x is just negative cosine of x plus c. And now, when you have multiple integrals, all added or subtracted together, you can just put one constant of integration there in the end. It doesn't matter. They will just absorb each other. So now if we simplify, we're just going to get x to the 4th over 4 minus cosine of x plus c. There you go. Okay, so now this last one is probably the hardest one that we've looked at yet. And you might be thinking, we've got quotients, blah, blah, blah. Is there a quotient rule for integration? Unfortunately, there's not. So for right now, you always want to try and rewrite it to look like a power rule. So what we can do is, because there's only one term in the denominator, is we can write this as 1 over x to the 5th plus x cubed over x to the 5th. We can just split up our fraction. And then all we have to do is split up our integral and simplify inside of it, and then use our power rule. So 1 over x to the 5th, we can just go ahead and rewrite that as x to the negative 5th power dx plus x cubed over x to the 5th. All of these can cross out, and they can leave us with an x squared in the bottom, which is just going to be x to the negative 2 dx in the next integral. And then all you have to do is apply your power rule. So when we apply the power rule to negative exponents, be very careful that you're still adding. So this is still going to be x to the negative 5 plus 1 over negative 5 plus 1 plus, do the same thing over here, going to x to the negative 2 plus 1 over negative 2 plus 1 plus c. So you want to be really careful that even though there's a negative sign on your exponent, that you still add 1 to it instead of subtracting 1. So now we're just going to get x to the negative 4 over negative 4 plus x to the negative 1st over negative 1 plus c. And if we just simplify this a little bit, get rid of those negative exponents, we're going to get negative 1 over 4 x to the 4th minus 1 over x plus c. Just rewriting our negative exponents in the denominators. So that's a really quick and basic lesson on doing simple integration. So that power rule is going to be really important for you when to start memorizing it and getting very familiar with it. Okay, so thank you so much for watching. Have a great rest of your day.